When you tap your screen, it feels instantaneous. But behind this seamless experience is a complex chain of events known as touch-to-photon latency. By 2026, technology has pushed this response time to between 8 and 12 milliseconds, effectively vanishing the perceived delay. At this speed, the delay is well below the human threshold of perception, creating the illusion of direct physical manipulation. But how is such precision actually measured and maintained? Let's explore the underlying architecture. Under the glass lies a grid of transparent conductive electrodes, usually made of indium tin oxide. This conductive layer creates a uniform electrostatic field across the surface of your device. It is this intricate, invisible structure that enables the screen to detect your lightest touch. Electrostatic fields are generated across the entire touchscreen grid. This invisible layer of energy is what makes your device responsive. Because the human body is conductive, bringing your finger near the glass introduces a new charge into the system. When contact occurs, the electrostatic field is locally deformed, causing a sudden spike in capacitance at that exact coordinate. Touchscreens use two primary methods to track your finger. The first is self-capacitance, which measures the change on a single electrode line. It is simple, but struggles when multiple fingers touch the screen simultaneously. The industry standard is mutual capacitance. Here, the controller measures the charge at the specific intersection where row and column electrodes cross. This grid-based matrix creates a unique signal for every intersection. By monitoring these points, the device can track multiple touch points across the entire screen simultaneously with extreme precision. This approach is what enables complex gestures like pinching and zooming, making it the foundation of modern multi-touch technology. Detection speed is determined by the polling rate. Modern devices scan the touch grid at frequencies up to 1000 Hz. A 1000 Hz polling rate means the sensor checks for your finger position exactly once every single millisecond. By scanning at such high frequencies, the latency between your physical touch and the device's awareness of that touch becomes virtually imperceptible. Modern screens use edge AI processing integrated directly into the sensor layer. This allows the device to filter raw input before it ever touches the main CPU. The sensor layer is constantly bombarded by noise from environmental interference and accidental touches. When a valid finger tap is detected, the MPU core instantly filters out the surrounding noise, ensuring only intentional input is processed. This reduced, high-quality data is then passed to the main processor, significantly lowering latency and power consumption. Palm rejection is a critical layer of artificial intelligence that keeps your touchscreen responsive only to your intent. When you tap with a finger, the system detects a sharp, localized change in capacitance, which it marks as a valid input. However, a palm resting on the edge creates a large, irregular, and diffuse contact area that the AI processor immediately flags. By analyzing the shape, pressure, and trajectory, the hardware ignores these broad contact points, ensuring your palm doesn't trigger accidental commands. For modern foldable and rollable devices, we utilize AHT, or silver halide transparent films. Unlike rigid sensors, these thin films offer exceptional flexibility. These films maintain perfect electrical conductivity, even after being folded hundreds of thousands of times. With a lifespan exceeding 200,000 cycles, AGHT films ensure your device remains responsive and free of touch dead zones, regardless of how often you fold it. Graphene is the new frontier in display technology. While traditional indium tin oxide, or ITO, is brittle and thick, graphene is a single atom-thick lattice of carbon. Because graphene is incredibly conductive and transparent, it allows for integrated force touch sensing directly within the display layer. This eliminates the need for bulky, extra hardware layers. By moving to graphene, devices can become thinner and more responsive than ever before. Modern touchscreens don't just react to where you are, they predict where you are going. By analyzing finger trajectory, machine learning models estimate the path before the tap is complete. This predictive capability allows the UI to pre-render the target state, effectively reducing touch-to-photon latency to near zero. By anticipating the interaction, The system ensures the display feels immediate and fluid, bridging the gap between hardware and software response. Modern touch sensors are incredibly sensitive. They can detect the microcapacitance of a finger even before it touches the glass. When a finger enters the detection zone, usually 1 to 2 centimeters above the display, it causes a subtle distortion in the electrostatic field. This enables pre-tap effects, such as highlighting buttons or previewing content before physical contact is ever made. By bridging the gap between hover and touch, devices can offer a more fluid and responsive user interface. Constant high-frequency scanning of a touchscreen drains battery life quickly. To solve this, modern devices use energy-aware, event-driven polling. In standby mode, the sensor grid enters a low-power sleep state, periodically emitting a faint, low-frequency pulse to monitor for proximity. As soon as the hardware detects a nearby object, it signals a wake-up event, immediately shifting into high-frequency active mode. The system now initiates a 1,000 Hz scan across the grid, ensuring lightning-fast touch detection only when it is actually needed. This smart resource allocation preserves battery while maintaining the instant responsiveness that modern users expect. Traditionally, touchscreen controllers were separate chips located on the motherboard, requiring signals to travel across the device. Modern designs bake the controller directly into the system on chip, or SoC. This eliminates the physical distance signals must cover, speeding up responsiveness by 15 to 20%. By bringing these components closer together, we drastically reduce system latency, providing a snappier user experience. Apple's Neural Touch engine dynamically adjusts the screen's polling rate to optimize performance and battery life. When you are reading static content, the screen polls at 60 Hz, conserving power while maintaining smooth performance. However, when high-speed interaction is detected, like in gaming, the engine kicks into high gear, scanning at 1,000 Hz. This intelligent shifting allows devices to offer pro-level responsiveness only when needed, effectively balancing peak speed with efficient energy consumption. Rollable displays present a unique challenge. As the screen expands or contracts, the geometry of the capacitive grid changes, which can lead to touch inaccuracies. Samsung's Roll Flex technology employs real-time grid recalibration. As the screen surface moves, the system instantly recalculates the sensitivity of the capacitive mesh. By adjusting the electrical field parameters dynamically, the controller maintains consistent touch accuracy across the entire surface, preventing the creation of dead zones. This ensures that every tap, whether the screen is fully retracted or extended, is registered with high precision. Hardware responsiveness is only half the battle. We define touch-to-photon latency as the total time elapsed from a finger hit to the pixel physically changing color. The signal travels from the hardware sensor through the operating system kernel. The real challenge lies in synchronizing the kernel with the display driver. This complex handoff is often where the most significant delays occur. Only after this synchronization does the command reach the display, creating the final photon emission perceived by your eye. Visual synchronization ensures that the graphic response, like a ripple effect, aligns perfectly with the hardware detection of a touch. When a finger interacts with the capacitive layer, the hardware triggers a sensor signal at that exact coordinate. This electrical signal is sent to the processor to identify the input location. The system then triggers a frame render at the same coordinates, creating the visual ripple effect that users expect. High refresh rate synchronization ensures that the delay between the physical touch and the pixel change is imperceptible. The next frontier in touchscreen evolution is predictive intent. Future AI will learn your specific typing patterns. By analyzing your trajectory, the system dynamically adjusts the hitbox of keys, making your input virtually error-proof. The AI anticipates where your finger will land, pre-registering the touch before contact is even fully confirmed. This predictive layer ensures seamless interaction, adapting to the user in real time. Touchscreens often face electrical noise from chargers or humidity, which can distort the capacitive grid. To maintain accuracy, screens use high-frequency filters. These isolate the actual touch signal from environmental interference. Once filtered, the touch grid returns to a clean state, allowing for precise detection even in challenging environments. To ensure instant response, engineers perform rigorous latency testing. A robotic finger descends to tap the display, while high-speed sensors capture the precise moment of physical contact. Simultaneously, we measure the time until the display registers a change. The goal is to keep this touch-to-photon latency under 15 milliseconds. Continuous software refinement ensures that our devices feel responsive and fluid, hiding the complex electrical signals happening beneath the glass. Touch technology has traveled a long path. We've moved far beyond simple grid detection. We are now in an era of predictive intelligence. The device no longer just waits for your input. It anticipates your intention before your finger even makes physical contact. This marks the transition to truly seamless human-machine interaction, where technology becomes an extension of human intent.